Welcome everyone. For today's prep, we're gonna be starting a new differentiation rule. Actually, one we've seen before in some form. This one's called chain rule, and we're not going to actually get to the rule today. What we are going to look at though is the type of function that we need to have in order to use this rule. And the type of function we're going to be considering are composite functions. So normally when we have a function, there's like addition and subtraction, multiplication, division, multiplying by constants, things like that. Composition of functions is a little bit different. So we're going to first go through the definition for what a composite function actually is, and then we'll get a little practice kind of working with this definition. All right, so first of all, what is a composite function? So we say a function h is the composition of functions f and g, provided this new function h of x is, well, we use this notation for composition. Well, a few different ways. So this little open circle, the way we read this is f composed with g. Now, how we actually calculate the composite function is we view function f as what we call the outer function. So function f here, this is our outer function. And the inner function is, well, the stuff inside. So g of x here, we would consider the inner function. So the idea behind a composite function is we're taking one function, the result from one function, and then we're plugging that into a second function. So you can kind of think of a composition as almost like an assembly line. So let's suppose that we start with our input x. So we've got our input x here. And based on this formula, the first thing that happens to that x is it gets plugged into function g. So we're going to send this input to function g. And you can kind of think of functions as it's just a machine on our assembly line. So we send it to function g. G does its thing, and then it spits out g of x. So that's the output from function g. Okay. Well, then this just continues on the assembly line, and then it makes its way to function f, machine f on our assembly line. And what does f do? Well, f is going to take this input, and f is going to do its own thing to it. And the final output here is f composed with g of x. That's the final output. So one way to view a composite function is it's the end result of this entire assembly line. So we're taking x, and then we're just seeing what we get after it goes through this entire process. So this is how we can view our composite function. All right, so that's the idea, that's the definition. Let's actually see some examples to get a better idea of what's going on. All right, so let's look at the first example here. We have a function f of x, which is the square root of x, and then we've got a function g of x, which is 4x squared plus 5 over x. And we're going to calculate two different compositions. So in the first one, we're going to calculate f composed with g of x. And then in the second one, we're going to switch it around. We're going to calculate g composed with f of x. And what we're going to see here is that the order actually does matter. All right, so let's start with the first one. We want to calculate f of g of x. Okay, well, let's start with that inner function. So let's replace that inner function. What do we know g of x is? It's this whole thing. So let's fill that in. So we'll still got our f. And then we've got our 4x squared plus 5x, 5 over x. Okay. So now, what are we going to do? Well, now we're going to take this whole thing, this whole 4x squared plus 5 over x. We're going to take that whole thing and we're going to plug it into function f. So wherever we see an x here, we're just going to swap that out with this entire thing. So wherever we see an x here, replace this x with this, replace this x with that. So we got a square root. And normally f would say this is just going to be square root x, but it's not just going to be x, it's going to be all of this. So it's going to be 4x squared plus 5 over x. And this is our composite function, the result. All right, so let's try the next one. So let's look at g with f of x plugged in. And we'll start it off the same way. Let's take our f of x. Now, what was f of x? Now we're just going back to the original version here. So f of x was just square root x. So let's fill that in. So we're just replacing f of x with what its original formula was. And then, now we're going to take this result and we're going to plug it into function g. So wherever we see an x in this original formula for g, we're going to replace it with square root x. So if we do that, we get 4 square root x squared plus 5 over square root x. So all we did is wherever we saw an x, back up in our original function here for g, replaced it with whatever we were trying to plug in, so square root x. Very similar to what we did back up here with f. So we replace that with the 4x squared plus 5 over x. And we're good. We've got our function. If we wanted to, we could simplify a little bit right here, but perfectly fine. So what we notice, though, is that the order actually does matter. So the order in which you do the composition, the order matters. So usually f composed with g of x does not equal the opposite one, g composed with f of x. Normally they're different. And that should make sense. If we go back to our assembly line analogy here, if we swap the order of our machines, so if pretending that this is like a car that's going down the assembly line, if we swap the order of the machines, you would expect to end up with a different result, potentially. So the order in which we do these things does actually matter. All right, so let's try another type of investigation of composite functions. And this is probably more of what we're going to be doing. So what we have here is a function. Looks like just a regular function. We've worked with these kinds. But what we're going to do for each of these is we're going to write each of these functions as a composite of two simpler functions. So we're going to try to break this function apart. Whereas in the first example, we had the two easier functions, the two kind of pieces, and we combined them into one more complicated function. What we're going to be doing is kind of reversing that. We're going to take the complicated function and we're going to try to break it up into its two simpler functions. All right, so how are we going to do this? Well, we're going to start with what we call the inner function. And then once we figure that out, then we'll find the outer function. All right, so let's call our inner function g of x. And then we'll call our outer function f of x. All right, so the way we find the inner function, usually this is, as the name kind of suggests, it's the stuff that's it's inside. So if you see parentheses or if you see a power function, it's all the stuff that's inside the parentheses or all the stuff that's inside the power function. So if we're looking in this first one, we've got a nice juicy set of parentheses here, and we've got all that stuff that's inside it. So that's what we're going to let our inner function be. X to the power 5 plus 9x plus 3. So we're looking inside the parentheses. Okay. Now imagine just replacing all of that with a single variable. So now we want to get the outer function. So we're just going to imagine, let's just call all of this just a single variable. So we're going to kind of just tighten it up, swallow it up. All this gets swallowed up into one variable. And what do we have left? Well, we've got the parentheses, and then we've got the raised to the power 8. And we're just going to make, again, that inner function into a single variable. So we're just going to call that all just simply x. So our inner function, the stuff that happens kind of first, is this polynomial. And then the outer function is the power function here. So let's try one more of these. Let's look at the next one. So we've got this function k of x, and it's the square root of 4x squared minus 5. So again, we're going to do the same approach. We're going to look for the inner function first, and then we'll figure out the outer function. And as usual, whenever we have a root function like this, it doesn't hurt to just first rewrite it as a power function. So we could rewrite this as 4x squared minus 5, all raised to the 1/2 power. And now we see we're kind of in the same, we have the same idea. So we're going to find the inner function, and then once we have that, we'll get our inner function. Or our outer function, rather. All right, so what do we got? Well, we got a nice set of parentheses. Look at the stuff that's inside the parentheses. So in this case, it's 4x squared minus 5. So we're going to let our inner function be the 4x squared minus 5. And then what do we have besides that? What do we have left? Well, we've got the parentheses, and then we've got this raised to the 1/2 power. So that's going to be our outer function. And then we just got to give a variable here. So we're going to use x. You could use a different variable. So if you wanted to, you could make this u. But we're going to use x. Doesn't really matter. So this will be x raised to the 1/2 power. So a lot of times, the way you identify the inner function, you just look for what's for parentheses, and you look for what's in the parentheses. So we've got our two simpler functions in each of these. And what we're going to look at in class is how to differentiate these types of functions. And we'll go through the rule right now, but we'll get some practice with it in class. So the special rule that helps us differentiate these composite functions is called the chain rule. And we've actually seen this before already. We saw a special case of it, rather, called the general power rule. So let's just read through the chain rule and see what it's telling us. So first of all, it's telling us how to differentiate a composite function, f composed with g of x. So it's telling us how to do that derivative. All right, so let's see. And again, we've got the outer function, and then we've got the inner function here. So we've got our outer and our inner. So what are we going to do? Well, the first step for chain rule is to differentiate the outer function. So that's going to be our step 1. So we differentiate our outer function. Step 2 is to keep the inner function exactly the same. So we keep the inner function that's being plugged in exactly the same. We don't make any change. Okay. We still do have to eventually differentiate that inner function, but that comes at the end. So after we've differentiated the outer function, we've kept the inner part the same, then we're going to multiply by the derivative of the inner function. And this is precisely what we've seen in the special case that we called the general power rule. So what did we do in our general power rule? Well, here, the outer function was the power function, and the inner function was all the stuff inside the power function. So how did we do our general power rule? Well, first step was to differentiate the power function just like regular. So we bring down the exponent, and then we subtract 1 in the exponent. So regular power rule kind of stuff. Then we kept the inner function exactly the same. So there was, kept the stuff inside the parentheses exactly the same. And then we multiplied that result by the derivative of the inner function. So this is what we've been doing. So general power rule is a special case. And what we'll be doing in a few weeks is we're going to be starting to look at some other functions, exponential and log functions. So we'll see that we can still use the chain rule for working with those types of functions as well. So it's not just power functions that we can differentiate with this. We're going to see all different types of composite functions we can work with. All right, so in class, we'll get a little practice actually applying the chain rule, but it's going to feel very similar to our general power rule so far, because that's really all the types of functions we've worked with. So we'll see you then. Bye-bye.